Welcome back from spring break. As you may or may not know, we have some more breaks coming up in the next few weeks. We have Easter coming up on April 1st, that's no joke. And we have the Good Friday before that, that would be what, March 30th? And then the Monday after Easter, April 2nd, we have those off. There's another day off, I think it's maybe the 11th of April. That is advising day, so signing up for next semester. I do want to make up the time you missed by not having class the last couple days before spring break, so I'm probably going to make some videos. You don't have to attend, but I'm probably going to make some videos about content around Easter time and maybe around the time where we have the advising day. Not that I'm going to give you more problems to do than normal, but just so we can get through the content better. You can expect the same amount of problems. And I think I'd like to even give you a little bit more of a break than you've been getting. I think probably from this point on, you won't have to do all the completion problems. There will be a certain proportion to give you a little bit of a break. And probably as we get close to the end of the semester, we'll get even more of a break, and you can just do as many completion problems as you want, meaning you wouldn't get credit for those, but that'll be maybe the last week or two of class that will do that. You'll still have a graded problem or two to do, but that will give you a little less pressure to do as much as you are required to do. What's the plan for today? Well, first of all, I think we should review. And it is going to be mostly review with extra details. Because, you know, it's been 2 weeks. Maybe you have completely forgotten about algebraic structures in those 2 weeks, or you feel like you have at least. And so we are going to talk about, for the most part, things we've already talked about, but more in depth, especially with regard to cosets and Lagrange's theorem. I would highly suggest watching those extra videos from Socratica, a web channel on YouTube that goes over Lagrange's theorem. That's one video, it's about 9 minutes or so. And then there are a bunch of others, I think maybe 27 of them you can pick and choose from content that we've done so far to watch to help you review as well. In lecture 15a, I want to just quickly, first of all, review the idea of the group of automorphisms of group G and the group of inner automorphisms of group G. Maybe talk briefly about what to expect maybe on the next exam related to that, things you should know. We'll delve more deeply into cosets and their properties, and you definitely want to get good at remembering these properties. There are a lot of them, but you want to get them internalized. And then lecture 15b, we'll look at Lagrange's theorem again and applications, including something new called the orbit stabilizer theorem, and an introduction to something called external direct products, hopefully at the end if we have time. Okay? So reviewing odd G and in G, remember, given any group G, finite or infinite, doesn't matter, it's just a group, you can define a new group. That's an interesting concept. Given any group G, you can define a new group, call it odd G, the group of automorphisms of G. What is an automorphism? Does anybody think they can define an automorphism for me? I'm not going to do an official definition here. But what property do automorphisms have? What properties?
It's an isomorphism that maps itself to itself.
Okay, that's a definition essentially.
Okay.
It's an isomorphism from a group to itself. That's essentially the definition of an automorphism. That's right. So what properties does it have? It's going to be one-to-one onto operation preserving, OP, standing for operation preserving. And fourthly, although I probably should put it first, it maps the group G to itself. It's an isomorphism from the group G to itself. Okay? Every automorphism is an isomorphism. Never forget that. Okay? It's a special kind of isomorphism from group G to itself. It forms a group too. The set of all automorphisms from a group G to itself forms a group that we call odd G. It's a group under function composition. The elements of odd G are functions. And the operation is composition. What should you know or be able to do on the exam related to this? Probably proving it's a group is, well, maybe a little bit just unpleasant. You need to verify closure, that the composition of two automorphisms is another automorphism. Got one automorphism and another automorphism. The composition certainly is going to map G to itself. So it is a possibility for an automorphism. It's satisfying property 4 here. Does it satisfy 1, 2, and 3? 1 and 2 are pretty quick from a theorem back in chapter 0. Right? The composition of two one-to-one functions is also one-to-one. The composition of two onto functions is also onto. Would I have you prove that from scratch? Well, probably not. It's kind of beside the point at this stage. So you could probably just refer to that. Proving it's operation preserving, the composition here. We did talk about that one day. It's just a quick calculation. The fact that beta is 1-to-1 or is operation preserving would give you this fact. Beta of G1 times G2 would be beta of G1 times beta of G2. And then you can use the fact that alpha is operation preserving. To write this. And that essentially does it. This thing over here is the same as alpha beta of G1 times G2. And this is alpha beta of G1 times alpha beta of G2. So alpha beta applied to the product G1 times G2 is the product of alpha beta applied to each element individually, G1 and G2. So you are using the fact that beta and alpha are operation preserving. So it's not too difficult, but a little bit of a pain. Associativity. You never have to prove functions are associative in this class from this point on. Okay, that is definitely something we verified in the past. It's pretty easy to verify. You can just, but it should be mentioned. You should say function composition is associative if I asked you to. It's part of the proof here. Does it contain the identity? What would the identity be? What's the identity of G going to be? Take a guess. It's probably right. Maybe I should even call it epsilon. What should I guess for the formula for epsilon to be the identity function? Hint, I've given it away by saying that. Maps an arbitrary element of G to what?
To itself.
To itself, yeah. Identity function. It's like f of x equals x. Okay? Under function composition, that's an identity. You compose this function with any other function. Alpha epsilon of G you get that function back. Alpha epsilon equals alpha. The identity function that maps every element to itself is the identity of this group under function composition. Is it really an automorphism? Yeah, it is. That's trivial. It's 1-to-1 onto. It's certainly mapping G to itself, and it definitely is operation preserving. By definition, alpha G1 times G2 is that. Also by definition, this gives you the same thing. Does every element have an inverse? What would the inverse of alpha be if alpha is an automorphism of G? Take a guess, it's probably right, I hope.
Alpha inverse.
Alpha inverse, the inverse function. Right? If alpha is 1-to-1 and onto, then alpha inverse will exist and also be 1-to-1 and onto. If alpha is it's mapping G to itself, so alpha inverse will map G to itself. Is it operation preserving? That was a bit trickier. Proving alpha inverse is operation preserving. We did in the general case of isomorphisms back in chapter 6. I guess we're still in chapter 6 here talking about this. I did verify that in one of the lectures. I don't remember if it was the one right before spring break or not. It's probably one of the last couple before spring break. You need the fact that alpha itself is operation preserving. You also needed the fact that alpha itself was 1-to-1, I believe. If you look back at that proof. That is a proof worth looking back. In fact, I think if there were any part of this proof that I'm describing here that I might put an exam to, it might be that very last one. And it works even for just plain isomorphisms instead of automorphisms. If alpha is an isomorphism from G1 to G2, then alpha inverse, it turns out, will be an isomorphism from G2 back to G1. G1 and G2 not necessarily the same groups, but isomorphic. Showing this is operation preserving, I think it's a fairly decent chance that could show up on exam 2. Compared to other possible proofs, it's got a good chance. Showing alpha inverse is operation preserving. Make sure you think about that. I did talk about it in lectures 12, 13, or 14, or one of those. There's another group you can consider called InG, the collection of all inner automorphisms. That's also a group under function composition. What is an inner automorphism? It's a special kind of automorphism. It does satisfy all these properties. It is an automorphism of G still. Obviously, if you think about it at least, InG must be a subgroup of odd G. Every inner automorphism must be an automorphism. There are special automorphisms that have a nice formula. Given little g, I think the book used little a in capital G, you can define a function phi sub a from G to itself by a formula phi sub a of x equals ax a inverse. Remember that? Of course, you need to verify this is an automorphism. You need to verify this is 1-to-1 onto operation preserving. It definitely maps from G to itself. X is an arbitrary element of G here in this formula. Is it operation preserving? Maybe we should check that. There's the output when we plug the product G1 times G2 into the automorphism that we're trying to show is actually an automorphism. Do we get the same thing if we apply phi individually to G1 and G2 and then take the product of those things? Yes, we do, because of the associative property. For extra emphasis, I'll put it in here like this. That's the identity, so this simplifies to A, G1, G2, A inverse, which matches. It is operation preserving. It is 1-to-1 and onto as well. It's an automorphism of G. A special kind, it's got a formula. Special kind of formula, not just any old formula. A special kind of formula. The key fact that makes this a group actually is the fact that you can verify that the composition phi A with phi B is the inner automorphism induced by the product A times B. That's the key equation to help you verify that this is a group. Is the identity in there? Yeah. The epsilon function is the same as phi sub E. The identity function is the same as phi sub E. Think about that. It's kind of a weird thing. And again, pretty much everything we're doing here in the rest of group theory is pretty weird. Chapter 6, 7, 8, and 9, and 10, the rest of group theory. It's pretty weird concepts, kind of foreign concepts you got to get used to. But again, the goal is to develop tools to help us do our classification of groups. Okay? It's not clear where these tools will lead us. It's maybe not clear, but that's the goal. It's worth noting that the group of inner automorphisms is trivial, meaning just the identity if G is abelian. If G is abelian, this formula simplifies to just the identity function. If G is abelian. Or in fact, if A happens to be in the center of G, remember the center? Earl Friend? Set of things that compute with everything in G. If A happened to be in the center of G, even if G was not abelian, this would simplify to the identity function. The identity inner automorphism, which is the same as this. So, in general, you might say in G is certainly smaller, so to speak, than G is. Certainly if G is finite, the order of the group of inner automorphisms of G is less than or equal to the order of G. Because you can get this kind of thing happening. And if G is abelian, the order of in G is just 1. It's trivial. Very quickly, just remind you that for every positive integer n, we have that the group of automorphisms of Zn is isomorphic to Un. I'm not going to go through the proof. I did that back, I think, in lecture 14. But basically, the idea is, say, take an example, Z12. Automorphisms, since they are isomorphisms, have to map elements of a given order to another element of a given order. Generators of Z12, in particular, would have to get mapped to other generators of Z12. It's just an example here. What are those generators? 1, 5, 7, and 11, right? Hey, that looks kind of familiar. Those are the elements of U12. Now, the elements of U12 are numbers, whereas the elements of aught of Z12 are not numbers, they are functions. But any given element of aught of Z12 would have to map the identity of, or generator of Z12, 1, to another generator of Z12, because they have to preserve orders, right? Order of Z12. The alpha of 1 would have to be 1, 3, or 1, 5, 7, or 11. Those are the generators of Z12. Those are the elements of Z12 that have order 12. They are also the elements of U12. The elements of odd Z12 have to have this property. And that essentially helps you define the isomorphism. You would take alpha, the alpha that maps 1 to 7, for example, and under the isomorphism between these two things, you'd map that function to the number 7. Maybe that makes sense to you, maybe it doesn't. It kind of depends on how awake you are and how well you can pay attention when you feel sleepy. Okay, it is worth thinking about. That's kind of the intuition behind why this is true. Make sure you spend some more time thinking about it. All right, let's delve back into cosets again. What is a coset? Well, first some notation. Aha and aha, remember that? Okay, you got H in general doesn't have to be a subgroup of G, though usually it will be when we're thinking about this notation. You can write this notation, AH, to be as a set, first of all, to be the set of all products of A with elements of capital H. If you think about it, that's going to have, if say H has order, say if H is a subgroup of G and H has order 10, then AH is going to have 10 elements as well, if you think about that. Because there's 10 different choices for the little h. And they would all just generate distinct elements A times H. If H is a subgroup of G, this is called a left coset of H and G containing A. It's got A in it because if A, capital H is a subgroup of G, it's going to have the identity. You can use E here for one of these. A times E is A. The left coset would contain A. So our terminology matches reality. The left coset containing A does truly contain A. This is called the right coset if H is a subgroup of G, though in general H is just a non-empty set. Set of all products like this, where A is now in the right. And then we've got this thing, AH, A inverse, is the set of all products like this as little h varies over capital H. And again, the terminology, if H does happen to be a subgroup of G, then again, AH is called the left coset of H and G containing A. And it does contain A, like I just said. Because if H is the subgroup of G, then H contains E. Again, A equals A times E. A also equals E times A. So HA is called the right coset of H and G containing A. The element A is called a coset representative of AH and HA, and A. I'm not going to usually do that. Just trying to help you stay awake here by saying aha and aha. We use this notation, order notation, to denote the number of elements in these sets. And again, well, H doesn't have to be a subgroup of G, though in this bullet we are assuming H is a subgroup of G. AH doesn't have to be a subgroup of G, even when H is a subgroup of G. Say that again. Even when H is a subgroup of G, the left and right coset, AH and HA, don't have to be subgroups of G. In fact, they're only subgroups of G if A is in H. I have to get used to this. I'm saying these things kind of fast. It's tough at this time of the morning. These are I can't emphasize enough. These are properties you want to start to know so well that when I say things like I just said, it doesn't go over your head. You're like, oh yeah, I remember that. Properties we're about to go over are listed if you want to look at them in the book on page 139. I will have them on the screen too. These are things you want to just get in your gut. You know, kind of like that. Kind of like derivatives in calculus. You see a function, you've practiced enough derivatives, you just know what to do right away. You want to know these properties. So here we go. These properties are essential, not just in chapter 7, when we use them to prove Lagrange's theorem, but also especially in chapter 9, when we talk about a new concept called a factor group. First of all, first property. A is an element of AH, and also of HA. I already mentioned that, because of this property here. And again, if H is a subgroup of G, the identity is going to be in H. So A can be written as A times a product of something in H, and a product of something in H times A. It's in both the left and right coset. You see their notation. That's probably the easiest one to realize. And it's fundamental importance, actually. Here's something else of fundamental importance. AH equals H if and only if A is in H. Imagine this blob represents the group G. And imagine this subblob represents the subgroup H. Imagine A is over here. Where is AH going to be in this picture? And where is HA? Where are they in this picture? I don't know for sure. This is an abstract picture where to draw them. It's just an idea, but wherever I draw them, they have to contain A. AH. And in fact, they will only equal the original subgroup if A is in H. If A is not in H, then these things are somewhere else other than H itself. So AH might be here, and in general, HA might be something like this. They could be different. These two things are not necessarily the same. But when they are the same, that's actually pretty important. And again, I'm saying AH equals H if and only if A happens to be in there. Let me go ahead and label that point B. B is in H. This fact is then implying that BH equals H. How would you prove this? It's not too hard. Any of these properties are, I think, fair game for proofs on the exam too. I'm not going to write detailed proofs, but let's just think about the ideas here. It's an if and only if, IFF. So we got two directions to prove. In this left to right direction, we have to suppose that AH equals H. The left coset of H and G containing A equals H itself, where H is assumed here in this properties list to be a subgroup of G. What's the goal there in this direction? The goal is to show A is an element of H. Well, it's essentially this equation again. A equals A times E. H is a subgroup of G, so the identity is in capital H. This is therefore, as property 1 says, in A times H. In fact, I could just apply property 1 here. But I'm assuming that equals H. And therefore, A is indeed an element of H. It's almost too easy. It's confusing, right? Sometimes things are like too easy, it gets confusing. You're not sure if you're really done. That is the idea of the left to right direction. What about the right to left direction? What if we assume, suppose, A is an H? The goal would be to show that these two things are equal. All right. To prove the first set inclusion, assume you've got an element, call it B, say, in the left coset of H and G containing A. The goal would then be to show that B is an H. You've got to use your assumption. A is an H. That's jumping the gun. B equals A times little h for some little h in capital H. But now, yeah, closure does it. Both little a and little h are in capital H, and H is a subgroup of G. We're still supposing that. Therefore, this product AH is also in capital H by closure. And therefore, B is in H by closure. Closure implies B is in H. The other direction technically still takes proof as well. To prove AH contains H, I'll write them backwards in subset thing. Assume you've got an element B in H. And show it's in this left coset. show it's A times something in H. Essentially solve this equation for x and hope that x is in capital H. That's equivalent to x being equal to A inverse B after multiplication on both sides on the left by A inverse. Is A inverse B in capital H? Yes. I'm still in this direction supposing A is in H. So A inverse would be in H. H is a subgroup of G. And I'm supposing that B is in H. Closure would imply this thing's in H. A inverse B is in H. And A times A inverse B is A inverse B is B. Therefore, B is A times something in capital H, which is what I wanted to show. I assumed B was in there. I want to show it's in there. I want to show it's A times something in capital H. That does it. B is A times something in capital H. That does it. Therefore, these two things are equal. AH equals H. It's like H is taking anything that's in it and pulling it into itself, so to speak, with this notation. It's like it's sucking in it. It's like A gets sucked into H. You can even make a slurping sound if you want. That was a bad one. Bad slurping for all time on YouTube. I don't think I better try it again. H sucks A into itself whenever A is an element of H. Okay? I feel like trying again, but I'm just going to botch it again. It's sucking it into itself. If A is not an H, then it doesn't get sucked into it. It's like a black hole or something. Okay? But only if A is an element of H. It doesn't do it when the elements are not in H. There's an associativity kind of property. Doing it on time. This always takes longer than I would hope. There's an associativity kind of property. The left coset of H in G containing A times B is the same set as, well, A times BH, where BH is the left coset of H and G containing B. You can put the parentheses in either spot. And actually here, with this notation here especially, this is where it's important, where on the previous slide, H did not have to be a subgroup of G. Here on this slide, H is a subgroup of G. But BH is not necessarily a subgroup of G. It only is if B is an H. So I can still use this notation. I can still write A times this set, so to speak. Say the word times loosely. Where this set is not necessarily a subgroup of G. But these two sets are the same set. Is the point. And that actually is a real important thing as well in chapter 9. Two cosets are the same if and only if A is an element of BH. You could also say if and only if B is an element of AH. You could also say if and only if B is an AH. So the symmetry. Because we're low in time, I don't want to prove that, but that's something you can take to the bank. Moreover, for any A and B, these two sets are either equal or they are disjoint. In other words, their intersection is empty. Also very important. In this picture, let's just talk about left cosets here. Distinct left cosets have no overlap. So for different cosets representatives, different A's and B's, either this is true or this is true. They partition G. And it's not any old partition, it's a very special kind of partition. The number of elements in each of these cosets is the same. They partition G into subsets of the same size. And if G is finite, these would definitely be finite sizes. And you also have this thing, here I skipped. AH equals BH if and only if A inverse B is an element of H. This is not a rigorous argument, but essentially, to see this, I can easily make this rigorous. Essentially, to see this, you imagine multiplying both sides of this by A inverse. You can make this proof pretty easily. Use the associative property now. That's the identity, which is going to be an H. This is all going to equal H. And these two things will be the same by property 2, if and only if the thing in front of the H there at the bottom, A inverse B, is an element of H. By property 2. So property 2 can be used to prove this. These are all really, really fundamental importance. It's about quiz time here. I know it's really, really tough here at such an early hour to get these things. It's something definitely to work really hard on. It's definitely going to make the content from here on out easier for you. Let's take a quiz.